Hello and welcome to the Work Package 2 presentation part regarding frequency support from multiple offshore wind power plants and its exchange between synchronous zones. My colleague Dr. Ali Bidadfar and I, Markus Kaiser, will present our research results regarding frequency support in the frame of Work Package 2. I received my bachelor and master degree in electrical engineering at RWTH Aachen University and work as a research assistant since May 2016. Within promotion, I'm researcher at Work Package 2 and 16. First, I will start with the exchange of frequency containment reserve via HVDC grids connecting multiple synchronous zones, which could be, for example, Great Britain, Northern Europe, and continental Europe. Later, Dr. Bidadfar will present his work on frequency support from multiple offshore wind power plants connected through HVDC grid. As a consequence of increasing converter-based generation and less synchronous generation, the system inertia decreases and therefore the rate of change of frequency increases in case of power imbalances. As defined in the grid code, new HVDC systems and HVDC-connected offshore wind power plants have to provide ancillary services. Analyzing the offshore HVDC systems which already exist and which will possibly be built in future, two options resulting for frequency support. First, the exchange of frequency containment reserves between synchronous zones, and second, the support from multiple offshore wind power plants. Challenging for both options is the fact that frequency support will affect the overall HVDC system. In case of multiple converters connected to the same system, the grid code expects the provision of frequency containment reserves in one predefined system, as the current regulatory framework defines FCR per country. The implementation of frequency support can be communication-less and communication-based. At the communication-less implementation, the DC voltage is used as communication medium between converters, and usually group controllers are implemented decentralized at each converter. At the communication-based implementation, all necessary data is communicated to one centralized controller, and the calculated reference values are sent to all converters. In this presentation, I will focus on the communication-less approach. The overall aim is to be able to exchange frequency containment reserves between synchronous zones and offshore wind power plants to increase the overall frequency stability. In the following example, master-slave control, where one converter is controlling the DC voltage, is assumed. Additionally, an active power group depending on the DC voltage is implemented to share possible imbalances of the active power equilibrium within the HVDC system. The communication-less frequency support between synchronous zones extends this control by a frequency-dependent active power group and a frequency-dependent DC voltage group. As mentioned before, the DC voltage is used as a communication signal in order to trigger the active power support by the DC voltage-dependent active power group. This exemplary result shows the support behavior of a three-terminal HVDC system connected to two synchronous zones and a wind farm. The converter connected to the wind farm does not contribute to the frequency support. At the beginning of the simulation, the design fault of 3 GW loss of generation in continental Europe occurs. The DC voltage controlling converter reduces the DC voltage in order to communicate the active power demand to VC2. Due to the modified active power flow, the frequency in the Great Britain system changes. At 7.3 seconds, the frequency deviation exceeds the implemented frequency deadband. Subsequently, the different group controllers interact and the state of equilibrium results in a reduced exchange of FCR. This example shows that the inertia and the dynamic activation of FCR of each system influences the exchanged FCR. A compensation of this effect for unidirectional frequency support is possible when the AC system inertia and the dynamic of the FCR activation in the AC system is known.
Frequency support from multiple offshore wind power plants connected through HVDC grid. Frequency support from offshore wind is a requirement in most of grid codes. For AC connected offshore wind farms, the support is straightforward from technical point of view. The frequency deviation is measured in offshore side and power production is adjusted accordingly. However, for HVDC connected offshore wind farms, it is a different story. The onshore grid frequency deviation should be communicated to onshore side, either using a communication link or by adjusting DC voltage level and using it as a communication medium. We refer to this approach as autonomous frequency control, or AFC. The AFC is communicationless method. Each of these methods has been proven to be viable for point-to-point HVDC connections, but the feasibility of AFC in multi-terminal HVDC grids seems to be challenging. Here is the advantages and disadvantages of communication-based and AFC methods. With communication-based control, grid code requirements can be met, and pairing between each two AC systems is possible. This makes it possible, for example, an offshore wind farm to play in power market. Disadvantages of this method is that it is costly and also less reliable. The advantages of AFC are being reliable, cost-effective, faster response, and improving the system dynamics. But the challenges of AFC are significant. It is not straightforward to meet grid code requirements. Offshore wind farms cannot play individually in power markets. It adds complexity to system control. It brings undesired reactions to the wind farms and also undesired DC voltage variation in the HVDC link. There are some other challenges that we have analytically studied them in the paper referred as number 2 here. Proposed frequency control. A comprehensive control combining communication-based method and AFC. To mitigate the problems associated with both frequency control mentioned in previous slide, we have proposed a comprehensive method comprising both of the methods at the same time. To do this, here in this slide, the control scheme is shown in big picture for central control or control hub and for onshore and offshore HVDC converters. The control hub, or central frequency control, CFC in short, collects data from onshore grid and offshore wind power plants. These data include frequency deviations, available power, contracted power, grid code of each onshore grid, and so on. CFC determines how much power from which power plant, wind power plant, and onshore grid should be supplied to a disturbed system. The onshore HVDC converter is obedient to CFC unless a large frequency deviation, shown as LDF in the picture, is detected at local AC grid. In case of communication delay or failure, the AFC would be operational. For more info about the proposed frequency control, please refer to the paper provided in this link. To show the challenges of AFC and the benefits of the proposed control, we have simulated some operational scenarios on a 4-terminal offshore HVDC grid shown in here. It is proven that proposed control is beneficial in terms of power flow control through the HVDC grid and also protecting the system operation against collapsing under an HVDC converter outage. For more info, please refer to the studies that we have provided in the following link. Here are the conclusions for our studies. transport capacity in HVDC system must be ensured. The autonomous frequency control, or AFC, in HVDC grids with multiple synchronous zones can provide only unidirectional support. In offshore HVDC grids with wind farms, the AFC can have some technical challenges, such as difficulties in meeting grid code requirements. A comprehensive frequency control was proposed, including both communication-based and AFC. With the proposed frequency control, some possible targets are aimed, such as a predefined active power support between predefined regions and offshore wind farms, meeting different grid code requirements, minimizing overall frequency deviation, equalizing frequency deviation of supporting system, and finally boosting the overall system stability.